The proposed Train-Attention-Augmented Language Model (TAALM) is a novel approach to continual knowledge learning (CKL) in large language models (LLMs). It addresses the inefficiencies of standard training procedures by dynamically predicting and applying weights to tokens based on their usefulness. This method employs a metalearning framework that optimizes token importance predictions, facilitating targeted knowledge updates and minimizing forgetting. The authors argue that previous studies on CKL have primarily focused on methods such as regularization, architectural modifications, and rehearsal techniques to mitigate catastrophic forgetting. However, these methods inherit the inefficiencies of standard training procedures, applying uniform weight across all tokens, which can lead to unnecessary parameter updates and increased forgetting. The TAALM approach learns to predict weights that approximate importance, enabling targeted continual knowledge updates through a label-free metalearning method. This contrasts with the learning of causal LM, where the document is decomposed into multiple token sequences, each with different importance but uniformly weighted. The authors also introduce a new benchmark, LAMA-ckl, to address the issue of existing benchmarks not clearly exhibiting the trade-off between learning and retaining. Through experiments conducted on both newly introduced and established CKL benchmarks, TAALM demonstrates state-of-the-art performance compared to baselines and shows synergistic compatibility when integrated with previous CKL approaches. Large language models, LLMs, suffer from catastrophic forgetting, where they forget previously learned knowledge when updated with new information. Continual knowledge learning, CKL, addresses this limitation. This study proposes a novel approach, Train-Attention-Augmented Language Model (TAALM), to mitigate catastrophic forgetting. TAALM predicts token weights based on their usefulness for efficient knowledge update, leveraging a metalearning method to train a supportive model. This supportive model predicts weights for the base model, enabling targeted knowledge retention. The authors introduce a new CKL benchmark, LAMA-ckl, and demonstrate state-of-the-art performance on both LAMA-ckl and the temporal wiki benchmark. The TAALM approach is compatible with other CKL methods and exhibits a synergistic effect when integrated. This means that TAALM can be combined with existing approaches to further improve knowledge retention. The key innovation lies in the metalearning method, which enables the supportive model to adaptively predict token weights, optimizing knowledge update. The proposed approach addresses a critical limitation in LLMs, enhancing their ability to retain knowledge over time. By predicting token weights, TAALM enables efficient knowledge update, reducing the risk of catastrophic forgetting. The introduction of the LAMA-ckl benchmark provides a new evaluation framework for CKL methods, allowing for more accurate assessment of knowledge retention capabilities. Continual knowledge learning, CKL, is a variant of continual learning, CL, tailored for large language models, LLMs, aiming to incorporate new knowledge without catastrophic forgetting of previously learned knowledge. Existing approaches to CL and CKL can be categorized into three main categories: regularization, architectural, and rehearsal, all of which strive to minimize changes in parameters from initial points. Regularization approaches, such as L2 regularization, directly control the extent of parameter changes through weight regulation. Architectural approaches freeze base model parameters and expand learnable parameters with adapters, keeping initial parameters untouched. Rehearsal methods continually review data employed to train the initial model, returning parameters to their initial points. This paper introduces a novel approach, Train-Attention-Augmented Language Model (TAALM), which filters objective tokens to achieve the same goal of minimizing parameter changes. In the context of metalearning, which is understood as learning to learn, the metalearner is an LLM architectural model that predicts hyperparameters of the base model, with token weights serving as hyperparameters in the training objective. Token selecting methods, such as token dropping, focal loss, and row 1, have previously been explored to enhance learning by selecting specific tokens, assigning more importance to tokens with higher classification error. The proposed TAALM introduces token importance and token-weighted learning, TWL, where the TWL objective function is formalized in equation 3, assigning weights to log probabilities of each sequence, approximating the importance of each sequence. Token importance is defined as usefulness, indicating how much contained information is useful for solving related tasks in the future. Under this definition, a metalearning approach, train-attention, is proposed to predict token importance through metalearning, enabling the model to adaptively focus on relevant tokens and improve learning efficiency. A novel approach to optimizing a meta-learner, named train-attention, is presented for predicting optimal token weights for a base causal language model, LM. This optimization process involves two steps: learning and solving tasks. In the learning step, the base LM is trained on a dataset D and updated to theta. The train-attention model, denoted as phi, predicts the token weights WD from D. The solving step applies the revised model theta to solve a task TD, and computes the loss value L theta, TD, to quantify the performance on TD. The optimization of train-attention is achieved through an iterative process that updates both the base LM and the train-attention model. This process involves sampling a data pair from the dataset D, predicting the token weights using the train-attention model, and then updating the base LM and the train-attention model using the gradients of their respective loss functions. The architecture of train-attention is depicted in Figure 2a, which shows that it shares the structure of the causal LM but replaces the decoder layer with a linear layer of hidden size times 1 dimension. The integration of train-attention with the base model is illustrated in Figure 2b, forming the TAALM model. Algorithm 1 outlines the optimization process for train-attention, which includes initializing the base model and train-attention, sampling data pairs, predicting token weights, and updating the models based on their gradients. This process continues until the train-attention model converges. Figures 3 and 4 provide visual representations of the optimization process, showing how the optimal W leads theta closer to theta and how the train-attention model is updated in one step. Overall, this methodology enhances the performance of a base causal language model in solving various tasks. The Train-Attention-Augmented Language Model, TAALM, is a novel approach that leverages task-specific knowledge to enhance language model performance. This is achieved through a metalearning framework that optimizes the model's attention weights, allowing it to adapt more effectively to new tasks. The process involves updating the base model theta to theta through task-weighted learning, TWL, using token weights generated from the meta-learner phi. The meta-learner is then updated based on the task performance, L theta, TD. To prevent convergence to a single point, the model parameters are reset to their initial state after each update of phi. The authors introduce a new benchmark, LAMA-ckl, designed to assess the cross-lingual knowledge, CKL, performance of language models. This benchmark is tailored from the LAMA dataset and includes data from Wikipedia and Wikidata. It evaluates both plasticity, or the ability to learn new knowledge, and stability, or the ability to retain existing knowledge. In the evaluation phase, the model learns data in a TWL manner with the parameter of phi frozen. Experiments are conducted on two benchmarks, LAMA-ckl and Temporal Wiki. The corpus, evaluation setup, and training details for train-attention are presented, along with the test results within the proposed LAMA-ckl benchmark. This approach demonstrates the potential to significantly enhance language model performance by leveraging task-specific knowledge and adapting to new tasks through metalearning. The LAMA-ckl benchmark is introduced for evaluating the continuous learning and knowledge retention capabilities of large language models. A novel token-weighted learning method, train-attention, is proposed to enhance model plasticity and stability by adjusting attention weights based on token relevance to the task. The evaluation setup assesses model performance using 4 factors: top accuracy, epoch, not-o-forget accuracy, and total knowledge. In the train-attention setup, the training procedure requires data D and related task TD. For the LAMA-ckl dataset, evidence documents are assigned as D, and knowledge-based triples in a document of schematic form are assigned as TD. The perplexity of object tokens is assigned as the objective of phi. A heat map of token weights generated by train-attention reveals that it prioritizes entities of certain categories over words with general grammatical roles. A baseline setup is established using LAMA 27b integrated with QLORA, and various baseline methods are compared, including standard fine-tune, k-adapter, mixer-view, LoRa, rec-atom, and Rho-1. The results show that TAALM achieves substantial continuous knowledge learning performance, outperforming other baselines in ability and speed of learning. The method records the top accuracy among checkpoints of 30 epochs and achieves the highest total knowledge score, indicating its effectiveness in enhancing both plasticity and stability of large language models. The performance of large baseline models, specifically LAMA-27B, is evaluated using the LAMA-ckl framework. Figure 7 illustrates the performance of these models on the TOLEARN and NOTTOFORGET tasks, with the z-axis representing the learning epoch and the y-axis representing accuracy. Table 1 provides a detailed comparison of the performance of various baseline models, including fine-tune, QLORA, k-adapter, mixer-view, QLORA, rec-atom, QLORA, Rho-1, QLORA, and TAALM, QLORA. The evaluation indicators used in Table 1 are explained in Section 4.1. Notably, TAALM, QLORA, achieves an accuracy of 0.4290 on the TOLEARN task in just 4 epochs, outperforming the second-best method, Rho-1, QLORA, by a factor of 3.04. TAALM, QLORA, requires only 25% of the epochs needed by Rho-1, QLORA, to achieve this accuracy. K-adapter demonstrates the highest NFACC, indicating that it rarely forgets previous knowledge. However, its TOLEARN accuracy barely increases, suggesting that parameter updates rarely occur. This is attributed to the architectural difference between K-adapter and QLORA. When comparing only QLORA-based methods, TAALM shows overwhelming performance in all dimensions, learning the most, the fastest, and forgetting the least. The combination of TAALM with other methods is also explored, and the results show a highly improved capacity than the baseline alone. Specifically, combining TAALM with K-adapter demonstrates a considerable balance between stability and plasticity. Finally, the performance of ArXiv, Train-Attention, and standard fine-tune is compared. The results show that ArXiv, which targets only the necessary token, achieves an upper bound of performance, with top ACC and NFACC values significantly higher than standard fine-tune. TAALM approaches ArXiv's performance, achieving 78.2% of ArXiv's top ACC and NFACC. This demonstrates the substantial advantage of token-weighted learning on CKL. The research paper discusses the performance of train attention across linguistic models, TAALM, on 2 datasets, LAMA-ckl and Temporal Wiki. It highlights that TAALM maintains a similar level to ArXiv, indicating optimization close to the upper bound. The experiment on the smaller tiny LAMA-1B baseline shows that TAALM outperforms other baseline methods with significantly smaller parameter sizes and computational resources. In the Temporal Wiki experiment, the paper uses a small model, tiny LAMA-1B, and compares it with GPT-2 large, demonstrating TAALM's better performance, especially with QLORA-based and K-adapter-based models. The paper emphasizes the importance of training DIFFSET, the only changed part of Wikipedia, for best performance. Figures and tables provided showcase the comparison between ArXiv, standard fine-tuning, and TAALM on LAMA-ckl, as well as the performance of small baselines on Temporal Wiki, illustrating TAALM's superior performance across datasets and models. The experimental results on the LAMA-ckl benchmark demonstrate the state-of-the-art performance of the author's method, consistently outperforming baselines across all periods and both changed and unchanged TWIKIPROBES. The K-adapter-based models exhibit better performance than QLORA-based models, showcasing a substantial advantage over the baselines. Furthermore, the authors test the TAALM optimized for LAMA-ckl on the Temporal Wiki, achieving the second-best performance, which suggests robustness across different task distributions. The LAMA-ckl benchmark is essential in highlighting the contrast between plasticity and stability. The authors observe that both changed and unchanged performance tend to move in similar directions when learning DIFFSET, contradicting their initial assumption. This is attributed to the overlap of data in the diff set and the experimental setup involving extensive training on a large dataset for a single epoch at a low learning rate. To address this issue, the authors structured the LAMA-ckl by partitioning the dataset into variant and invariant subsets, further classified based on task accuracy measured by pre-update baselines. They conduct training over multiple epochs on a relatively small dataset to observe knowledge acquisition. The LAMA-ckl benchmark reveals a clear upward trend in the TOLEARN set and a distinct decline in the NOTTOFORGET set as training progresses, demonstrating the contrast between plasticity and stability. The authors acknowledge limitations and potential avenues for future exploration, including task specificity of train attention, the possibility of coping with other tasks, and broader impacts on enhancing the practicality of large language models, LLMs, and saving computational resources. It seems like there is no content to refine. Please provide the transcript for the explainer video summarizing the research paper, and I'll be happy to refine it according to the guidelines. Continual learning, few-shot learning, and language models are interconnected areas of research that have garnered significant attention in recent years. In the realm of few-shot learning, the meta-SGD algorithm has emerged as a prominent solution, boasting remarkable efficiency in adapting to new tasks with limited data. This algorithm's prowess is further complemented by the focal loss function, which has revolutionized dense object detection in computer vision by mitigating the issue of class imbalance. The concept of row 1, introduced in this context, challenges the conventional wisdom that all tokens are necessary for task completion. Instead, it suggests that a subset of tokens can be sufficient, paving the way for more efficient processing and task-specific optimization. Gradient episodic memory, a continual learning method, has also been explored for its ability to mitigate catastrophic forgetting and enables seamless knowledge retention. Language models have been recognized as potent knowledge bases, capable of facilitating text-to-text transformations with remarkable accuracy. By leveraging these models, researchers can tap into a vast repository of knowledge, unlocking novel applications and use cases. The significance of these advancements is underscored by the numerous research papers that have contributed to the growth of continual learning, few-shot learning, and language models. Notable among these are papers that have pushed the boundaries of meta-learning, episodic memory, and the application of language models in natural language processing tasks. The LAMA-ckl benchmark dataset is constructed by sampling one document per unit, ensuring each document exceeds 70 tokens and contains both subject and object entities. These documents are then truncated to 512 tokens. To assess the accuracy of knowledge-based triples, 4 models are employed: Tiny Llama 1.1b, Llama 27b, QLORA, and K-adapter. Units with perfect agreement among these models are selected for either the TOLEARN or NOTTOFORGET set. The NOTTOFORGET set is further subdivided into descriptive and schematic tasks, with separate sampling procedures. Figure 9 visualizes the distribution of relation categories across each dataset. Table 3 presents key statistics for the NOTTOFORGET and TOLEARN sets, providing insights into the composition of these datasets. This carefully curated dataset setup enables a comprehensive evaluation of knowledge-based triple accuracy, facilitating the identification of units that require attention. This research explores the relationships between entities in two sets, NOTTOFORGET and TOLEARN. The NOTTOFORGET set encompasses relations such as birth and death places, official languages, and professional affiliations, including place of birth, place of death, official language, and original network. In contrast, the TOLEARN set covers a broader range of aspects, including instances, positions held, fields of work, occupations, employers, and music genres. To evaluate the training of TOLEARN documents, we utilized a robust setup consisting of 8 RTX 3090 GPUs, with a global batch size of 64 and a total of 30 epochs. This configuration required approximately 25 minutes of GPU time. The learning rate was set to 1e4, leveraging the AtomW optimizer and a maximum token length of 512. This precise setup enabled us to delve into the complexities of entity relationships and uncover meaningful insights. By examining these intricate connections, we can better understand the nuances of entity relationships and their implications for various applications. The section discusses the accuracy measurement and the train-attention training details. It explains how accuracy is used as a metric to assess the efficacy of models in label prediction. The train-attention training dataset is selected from LAMA units with an accuracy below 0.5, ensuring no overlap with other sets. The dataset is adjusted to address an imbalance in the initial data. The training process employs small and large models from the LAMA family, integrated with QLORA, with a large model for the base model and a small model for train attention. The parameters are initialized using a normal distribution, and a single A100 GPU is used with a batch size of 16 achieved through gradient accumulation. The learning rate is set to 2e4, and the AtomW optimizer is employed for both the base model and train attention. The section also describes the baselines, including QLORA and K-adapter, detailing their hyperparameters and the number of parameters expanded. The authors present additional experimental results, focusing on the performance of small baselines on the LAMA-ckl benchmark. They evaluate the tiny Llama 1B architecture, a smaller version of the Llama 27B model, using various methods including fine-tuning, K-adapter, mixer-view, rec-atom, RHO1, and TAALM. The results, illustrated in Figure 10 and Table 5, demonstrate that TAALM outperforms the other methods, even surpassing the performance of large baselines. Furthermore, the authors investigate the combination of their proposed method, TAALM, with other baselines. Figure 11 shows that the performance of all baselines improves when combined with TAALM, indicating synergistic compatibility. The combination of TAALM with mixer-view achieves the highest top ACC and total knowledge among all variations, as seen in Table 6 and Figure 12. This is attributed to the application of train attention to both the train and review data, resulting in more stable training. The authors also analyze the trade-off between plasticity, TOLEARN, and stability, NOTTOFORGET, of the baselines, including the combined variations. Figure 13 illustrates that the combinations with TAALM are positioned in the upper right quadrant, indicating a minimal trade-off between updating and forgetting. These results suggest that the proposed TAALM method is effective in improving the performance of small baselines and can be synergistically combined with other methods to achieve better results. The comparison of baseline methods, both alone and in combination with the proposed TAALM method, is presented in Figure 11. Gray lines represent the performance of each baseline, while red lines denote the combination with TAALM. Solid lines correspond to the TOLEARN setting, and dashed lines represent the NOTTOFORGET setting. All experiments utilize the Llama 27B model and are evaluated on the LAMA-ckl dataset. Table 6 provides a detailed analysis of combining TAALM with other baseline methods, showing the effectiveness of combining TAALM with K-adapter, mixer-view, and rec-atom. Specifically, the combination of Rs, QLORA, plus mixer-view achieves the highest top ACC score of 0.4500 at Epoch 3, with a total knowledge score of 1.3512. The combination of Rs plus K-adapter plus rec-atom plus mixer-view yields a competitive top ACC score of 0.3140 at Epoch 25, with a total knowledge score of 1.2817. Figure 12 visualizes the performance of combining other methods with TAALM on the Llama 27B base model, tested on LAMA-ckl, highlighting the robustness of TAALM when integrated with other approaches. The authors conduct 5 independent runs using different random seeds on the training data loader, with results presented in Figure 14, demonstrating the consistent performance of the proposed method with error ranges at plus or minus 2 sigma. In large-scale models, a delicate balance exists between plasticity and stability. This trade-off is particularly evident in the LAMA-27B architecture. The concept of total knowledge, visualized in Figure 13, illustrates this balance as a zero-sum state where the sum of TOLEARN and NOTTOFORGET equals 1. This figure also demonstrates how learning can lead to less forgetting in more efficient systems. The performance of large-scale baseline models on LAMA-ckl is presented in Figure 14, showcasing error ranges for 5 random trials. This data underscores the significance of striking an optimal balance between plasticity and stability to achieve superior performance. The LAMA dataset, comprising knowledge-based triples and their corresponding descriptive sentences, poses a challenge for causal language models due to its unidirectional nature. To mitigate this issue, a new systematic format is proposed, rearranging the triples to better align with the requirements of causal language models and reducing noise in the train-attention learning process. In the context of the temporal wiki experiment, the corpus consists of 2 datasets for 4 periods. These datasets include Wikipedia snapshots and DIFFSETs, which are segments of documents containing changed information compared to the last period snapshot. The test datasets, T-Wiki probes, consist of knowledge-based triples and are used for evaluation. The original study demonstrated that learning only the DIFFSET results in better performance than learning the entire snapshot. Therefore, learning of DIFFSET is set as the default, and heuristic filtering is applied to remove empty texts and texts with more than 70% non-letters. This reduces the total number of documents per DIFFSET data from an average of 837K to 707K. Each T-Wiki probes consists of 2 parts. Changed, which contains knowledge-based triples with changed information compared to the last period, and unchanged, which contains retained information from the last period. The evaluation metric is the mean perplexity of object label words, and one dataset is updated for only 1 epoch. The study on predicting object labels in triples addresses the issue of high perplexity due to grammatical violations. To overcome this, the research adopts the schematic task format used in LAMA-ckl, following the settings and hyperparameters from Zhang et al. 2022. The train-attention training setup involves pairing data and tasks, and manually joining documents from DIFFSET with Twiki probes to create 5,235 pairs. The results on Temporal Wiki show a rare trade-off between plasticity and stability in the performances of changed and unchanged sets, contrasting with the LAMA-ckl benchmark, which exhibits a clear trade-off. Table 7 indicates that an average of 8.0% of the unchanged set has evidence documents in the DIFFSET of the corresponding period, suggesting a cumulative supportive effect. This complexity is a factor in observing stability. Experimental results on the Temporal Wiki benchmark using the tiny Llama 1B baseline are presented in the figure. This visualization displays the perplexity of the changed and unchanged sets before and after training, with distinct colors representing different baselines. The arrows illustrate the improvement in performance following training, showcasing the model's adaptability and enhancement on the benchmark. This graph serves as a visual testament to the efficacy of the training process, highlighting the model's capacity to learn and refine its performance. Let me know if you'd like me to refine the rest of the transcript or if you have any further requests.